This goal topic is called Inferring Properties of a Polynomial Function from its Graph. So when I opened up this ALEKS topic, this was a picture I got. Yours may look a little different, but we're gonna have a graph that is marked with some local minimum. I see some minima here, and I also see some maxima here. Maximum here and maximum there. So what are we doing here? Part A is asking over which intervals is the function increasing. So I'm going to go and highlight every part of this graph that is going up from left to right. So you see how this section right there, that's going up from left to right. This section right there is also going up from left to right. Again, like this last piece, like from 7 all the way to the right, is going up. So let me read the x coordinates of where these are happening. In between -8 and -10. So that's gotta be from -9 to, what number is that? -6. So the first interval where this function is increasing is -9, -6. Can't remember if you guys have to use U for union like this, or just I think you have to just do comma. But if it's union, let me know. I thought it was just comma. All right, let's keep reading. What about this section in the middle? This one starts at -2, right? This one starts at -2, so I'll write -2, comma, and it stops going up at what number? 3. So the second interval where the graph is increasing is -2, 3. Let me bring this down. Last interval, it starts going up again at what number? 7, right? And it keeps on going up forever to the right. So the last interval will be 7, comma, positive infinity. Not because it's going up to the, not because it's going up, but this positive infinity, here I use it to say forever to the right, okay? As you go like 1, 2, 3, 4, 5, 6, 7, 8, you know, as you keep on going to the right, like that's what I'm talking about with that infinity symbol. So that's it for 3 increasing intervals. Let me bring this one down. Next part is asking us to find where the function is decreasing. So let me see. It's going down from all the way to the left to -9. So that would be -infinity to -9. And here, when I say negative infinity, I'm not talking about up or down of the graph. I'm talking about forever from the left, somewhere far, far from the left. And to -9, this graph is going down. The next section where the graph is going down is from -6 to -2. -6 to -2. And the last section is going down is from, what is this? 3 to 7. 3, 7. So these are the 3 intervals where this graph is going down from left to right, okay? All right, let me put these over here. So that's the first, this is the second, and this is the last. Okay, now let's see what they are asking for part C. At which x value does the function have local maxima? So local maxima are where you go from increasing to decrease. So where we have red to the left and green to the right. So let me just mark these for you, okay? So here is the first local maximum. So this is the local max right here. And there's another one here, right? Right there. This is also a local max. And that's it, right? These two are the only points where the graph was increasing to the left and decreasing to the right. So I'm going to go and write those down. What were they asking for? they want at which x values does these local max happen. Well, it happened at x equals -6 and x equals what number? +3. So I'm going to say x equals -6 and 3. The next question is asking us, give me 1 second. So I found the local maxima, and now let me go find what's next? Local minima. Okay. Where are they? Local minima is where we have these valleys, the lowest points of these valleys. So going down to the left and it goes up to the right. So notice there is our first local minimum at 9, and another one right here. That's another local min. Is that it? Oh no, one more, sorry. There's one more right there. This one's also local minimum. So look at the numbers. It's happening at -9, -2, and +7. So let me write those down. The x values where local minima happen are -9, -2, and +7. Okay. All right. It says, what is the sign of the function's leading coefficient? Whenever you want to find the sign of a leading coefficient, you must look at the right end behavior. Okay? Look at the right end behavior. Oh, hold on. Where did that go? Sorry. So if you look at the right side of the graph, and if it's going up, then the leading coefficient is positive. If you look at the right end of the graph, and if it's going down, then the leading coefficient is negative. Look at the right end behavior. Let's go see. So go to the right side of the graph, all the way to the right. Doesn't matter like what the graph is doing to the left side, okay? Just look at the far right. See? This graph is going up. You notice? To the right, it's going up. The right end behavior is going up. Therefore, okay, I'll say up to the right. If it's going up to the right, then this has a positive leading coefficient. If the graph is going down to the right end, for example, if I make up a function, let me just draw something, okay? Let's say that you have a graph that goes like, but let's say you go down like that. That graph will have a negative and leading coefficient because the graph is going down to the right. So remember that. That's the only thing you need to look at when you're trying to figure out the sign of the function's leading coefficient. Now let's do the last one, which is asking for the degree of the function. Okay. Now I have to talk to you about something called a turning point too, but based on the end behavior alone, take a look. This graph is going up to the right and up to the left, right? It's both pointing up, okay? Up to the left. So you notice the end behaviors are the same, right? So when the right end behavior and the left end behavior are the same, see, they're both pointing up. What we can say is that the degree of this function must be even. Must be even. Okay. What I'm saying is the biggest exponent of this function must be an even number. Okay. When the right end and the left end are doing the same thing, it could be up, up, okay, because they're both pointing up, right? Or it could be down, down. if they are doing the same thing to the right or left, right and left, then the degree must be even. Must be an even number. So what you're going to do over here is cross out all the odd numbers. Out, out, and out. Okay? Because the end behavior is the same to the right and left, the degree must be an even number. So we have 3 candidates left, 4, 6, and 8. Now you have to look at the number of turning points. Look, degree must be greater than, degree must be bigger than the number of turning points you have in this graph. Turning points the graph has. Okay, so we're gonna go count how many times this graph turns. Okay, and that is just the local min and local max. How many of those black and pink dots do we have? We have 1, 2, 3, 4, 5. So this graph has 5 turning points. 2 local max and 3 local mins. If you do 2 plus 3, that's 5 turning points. So we have 5 turning points in this graph, right? Which means it's gotta be, the degree must be, the degree must be bigger than 5, okay? Okay, so can it be 4? Nope. Can it be 6? Yes, because 6 is bigger than 5. Can it be 8? Yes, because 8 is bigger than 5. So on this problem, you will have to select both 6 and 8. But that's how you can solve to do a topic like this. And this one in ALEKS is called Inferring Properties of a Polynomial Function from its Graph.